Welcome back, everyone, to another session. Today, we're going to talk about categorical data analysis. You remember that last session, I talked about two different classes of statistical tests, parametric versus non-parametric tests. And I said that once your data is not interval or continuous, you cannot use a parametric test. You need to use a non-parametric test. So categorical data is of a nominal scale, so it's not interval or continuous. So uh, so this session we're kind of dealing with a different types of non-parametric tests, which enable us to analyze categorical data. So this session we're only focusing on categorical data, not ordinal data. These are the objectives of this session. Um, so you will learn what a chi-score test is. A chi-score test is one of the main tests researchers use to analyze different types of categorical data. So today we're going to learn about two main types of chi-score test, the chi-score goodness of fit test and chi-score test of independence. So I'll talk about when we could use each of them, and then we move on to two other tests, Fisher exact test and the McNemar test. So there are situations uh, where you can't use a chi-score test, then we need to think about using other equivalent tests. So Fisher test and McNemar test are two of those types of tests. And then after learning how to do these things, um, I'll teach you how to report the results from these tests. If you're trying to apply one of these tests in your research projects, you also need to be able to extract the useful information from these tests and report them in your projects. And then you will also learn how to perform these tests in jamovi. Um, so what is a chi-score test and what are its different types? So a chi-score test uh, is a non-parametric test which enables you to compare a distribution in a sample to an expected distribution in the population. So so if you have a variable which is categorical and this categorical variable has different levels, and then you have participants in different levels, and you want to see, for example, whether uh, the number of people in these levels are distributed equally in your sample or not, you can do a chi-square goodness of fit test. But if you have, for example, two variables which are also categorical, you want to look at the relation between these two variables, you can use a different type of chi-score test, which is called chi-score test for independence, or some people also call it chi-score test for association. So if, for example, you measure a socioeconomic status of some people with aphasia, and you want to see whether this socioeconomic status has any relations with their degree, like whether, and the degree is also a categorical variable here, like MA, BA, PhD. And if you want to see whether these two variables are related or not, you can use a chi-square test for association or independence. So a chi-square test is a non-parametric test which you use for categorical data, and it has two types. A chi-square goodness of fit test tries to test whether an observed frequency distribution of a nominal or categorical variable in your sample matches an expected frequency distribution. Uh, I'll give you an example. We have a different data set to play with for this session. You can download the data set in the link provided in this slide. You can use this data set for chi-square analysis during this session. Uh, so, yeah, when it comes to chi-square goodness of fit test, you have a categorical or nominal variable, for example, such as socioeconomic status, which is also one of the variables in this data set. And then we have different levels of socioeconomic status, and we want to see whether uh, the different levels are kind of distributed equally in our sample or not. So if we have like low, mid, and high, and we have 30 participants in our sample, we want to see whether we have 10 low socioeconomic status, 10 with medium socioeconomic status, and 10 with high socioeconomic status. It's a very simple test, and we'll see how we can do it in jamovi as well. Now it's time to do null significance hypothesis testing with this type of test, which we're going to use Pearson's chi-square goodness of fit test. So uh, now you should have downloaded the data on your personal PC. And if you have a look at that, we're going to focus on socioeconomic status. And then the question is here whether the levels within the socioeconomic status are distributed equally in our sample or not. So first, if you remember from last session, first we need to start with the null hypothesis. So we need to state the null hypothesis of the study. So the H null, or which HO is kind of the short form of null hypothesis if you see it anywhere else. So the null hypothesis is that all three socioeconomic statuses are chosen with equal probability. So if we have three socioeconomic status, uh, each of them should be chosen with equal probability, which is 0.33. Like each of them has a chance of being selected with 33% chance. But at the same time, we need to postulate the experimental or alternative hypothesis, which is H1. So the H1 says that at least one of the SES probabilities, SES stands for socioeconomic status, is not 0.33. So there should be a difference in the frequency of occurrence in one of the levels in socioeconomic status. So once we have our null hypothesis and experimental hypothesis sorted out, we need to calculate the chi-square goodness of fit, which you don't really need to do this because jamovi will need it. But anyway, I put the formula here if you want to do it by hand too. After this, uh, you get a value, and then with that value, you now need to decide whether you can reject the null hypothesis or you kind of fail to reject the null hypothesis. So you have your null hypothesis formulated, then you calculate chi-square, you have a alpha level, which is a criterion. We always kind of select 0.05 in our field is the golden standard. So you have the alpha level, which is 0.05, and then you calculate your goodness of fit, and then you'll see whether with the value you get, whether you can reject a, a null hypothesis or not. Now we're going to do it in jamovi. Okay, I loaded the data into Jamovi. This is that data, the same data, where we have four categorical variables. Stress, sorry, SES stands for socioeconomic status, and then we have other variables which we will work with them later on. But for now, we're going to focus on socioeconomic status, and the question we're going to answer is whether the different levels are spread out equally within this variable or not. So we have three levels in this variable: high socioeconomic status, low socioeconomic status, and mid socioeconomic status. So before we do the chi-score test, the Pearson's chi-score test, we just do some descriptive statistics about this test. Okay, we'll put socioeconomic status here, and then we'll make a frequency table. So we also create a bar plot. I told you that if you have a nominal variable, you can create bar plots to better present your data. So if you look at the bar plot, you'll see that the number of people in the low socioeconomic status and mid socioeconomic status is higher than the high socioeconomic status. So let's go to the table here. We'll kind of see that out of 100%, 30, almost 37% would go into low and mid socioeconomic status, while only about 27% would go into the high socioeconomic status. So as you can see, the numbers here are not exactly the same. Uh, the difference between high and low and high and mid, you can see a difference between high and low and high and mid. So now the question is this difference big enough to reject the null hypothesis or not? So we see a difference. There is a difference here, but we're not sure whether this is a big enough difference to reject the null hypothesis or not. Then now let's go and do the test. So now we're going to work with the frequencies tab. Click on it. So under one sample proportion tests, select chi-score goodness of fit test, and then you'll have a window like this. So we're going to work on SES, put the SES into the variable box, and then very easy, very quick. And you could also click on expected counts. You could see here that if the null hypothesis was true, we expected 10 people in the high, 10 people in the low, and 10 people in the mid, exactly 33% in each level. Uh, but the proportions between the observed and expected are not exactly the same, so there are differences here, and then we want to see whether it's significant or not. So you just go to the table here, chi-score goodness of fit, and you look at the p-value here. So if you remember, before we conduct the analysis, we set our hypothesis, and then we set up our criterion, which was the alpha level. So our alpha level was 0.05. So we said that if the p-value is below 0.05, we can reject our null hypothesis. But here, the p-value is above 0.05, is 0.741. So that means that this small difference here in the proportions is not big enough to reject the null hypothesis. So the conclusion is that the levels are distributed almost equally in our data, although we see some minor differences, but these differences are not really big enough. So this is how you do the goodness of fit test, but sometimes you want to change your hypothesis. For example, sometimes um, before you start doing the analysis, you come up with some predictions. For example, you kind of predict that uh, the number of people in the high socioeconomic status uh, will be 1.5 times bigger than the low and mid uh, level. So you can easily come here to expected proportions and change the value here and click. So you go here, you go to the table here. So we expect that we kind of, before we started the analysis, we expected to see 1.5 times higher compared to the other levels. So if you go to the table, the expected frequency is changed accordingly. So we expected to see almost 13 people here, but we only observed 8. So is this a big enough difference? No. If you go to the p-value here, it says that although there is a difference, but this is not a big enough difference to reject a null hypothesis. So we can basically, or we can put it to 0.5. Again, is not significant. Let's go to low. So, so when I put this to 0.5 here, it means that I expected to see, like, if I expected to see a, a 10 people in the high group, I expected to see 5 people in the low group. So the number of people I expected to see in the low socioeconomic status group is half the number of people I expected to see in high and mid. And then you see it's very close to it's almost on the border. So if you go to the low in the table, we expected to see 6, but we observed 11, almost 2 times bigger. And this difference is becoming significant. Yeah, that's the way we do it. If you have if you think that the levels are not distributed equally before you start the analysis, you could kind of come to this tab, expected proportions, and change the ratio here accordingly and see whether the result is significant or not. But you need to approach this with caution. You need to have your prediction before you do your analysis. So you can't change these things after you do your analysis. You need to have predictions before you start the analysis. Otherwise, if you just come here and change these values and you see a significant p-value and you report it, that's absolutely wrong. They call it cherry picking. You kind of play around with your data to find a significant effect and report it. This is not something we want to do. So that's why we always need to have a null hypothesis. We need to have predictions before we start the testing, the statistical analysis. We only test that null hypothesis. Yeah, that's all. So this is how we report the results. First, we present some descriptive statistics. Here, you could see, based on the table from the jamovi. We can also put the table in the manuscript. And then we go to the uh, we go to report the result of the test. So before we report the result, we also could mention the null hypothesis here and mention what is the null hypothesis, what is it that we are testing, and then you kind of present the results. And here we have 3 elements in the results table: the chi-score itself, the value of the chi-score, and whether this value is big enough to reject the null hypothesis based on our alpha level, which we kind of selected 0.05, but this alpha level, this value here is bigger than the criterion we selected. And then we have another thing here, which is called uh, degree of freedom. Degree of freedom in this test is always the number of levels in your variable minus 1. So you have 3 levels, and minus 1 it will become 2. So it's a bit complicated concept. I don't want to talk about it now, but yeah, we have 3 pieces of information, and we also present it here like this. Yeah, not a good artist, but that's the most important part of the report. So you start with descriptive statistics, you present your null hypothesis, and then you present the values exactly like the way I did here. This is APA style. So you present it based on this style, and then you can add a simple sentence as the um, interpretation of the results. So you not only present the results, you but also try to interpret the results. After talking about the chi-square goodness of fit test, we now turn to the chi-square test of independence or association. The difference between these two types of chi-scores is that in the chi-score goodness of fitness, we only have one categorical variable, and we are only interested in the distribution of the levels within that variable. But when it comes to the excuse me. But when it comes to the test of independence or association, we basically have two categorical variables, and we want to look at the relationship between these two categorical variables. The example we want to work on, you should have downloaded the data so far. So the example we want to work on is that the question we are asking is that is there a relationship between the level of stress before treatment and recovery success or chance by people with aphasia in the data set we have? And this data set is made, is not real. So anything you see there may not be true in the real life. So level of stress is a categorical variable. So whether they were stressed or not. So it's yes and no. And recovery success or recovery chance is also categorical, divided into two, like whether the chance was high or low. So that's the question we're going to ask. So like any other test, if we want to do null hypothesis testing, we need to have a null hypothesis first. So our null hypothesis is that the level of stress is not related to recovery success in this sample. And then we set up our criterion, the alpha level, which is 0.05, and then we do the chi-square test of independence or association. We're going to do that in a minute in Jamovi, and then we'll get a number for our chi-score and p-value, and then we'll see whether we could reject the null hypothesis or we fail to reject the null hypothesis. Let's see how we could do the test in Jamovi. You go to frequencies again. Now, instead of one sample proportion test, you go to contingency tables and you click on independent samples or chi-square test of association. And then you'll see this window, and uh, we wanted to look at the relationship between stress before treatment and uh, recovery chance. So our null hypothesis was that there was no relationship between stress, the level of stress before treatment, and the recovery chance. and both of our variables were categorical variables. So that's what we could see here. So uh, we look at the before that, I think that we need to click on expected counts as well so that we could see the observed values and the expected values next to each other. So this is the contingency table. We first have a look at the contingency table. We'll look at the expected values and observed values across the cells. These are called cells. So we see some differences. See, for example, in the high recovery group, uh, people who had like no stress before the treatment, we kind of expected to see almost 9 people, but we saw 5 people. And we see the same uh, pattern, but opposite in the other cell. Then we look at the other cells. Yeah, we see some differences in the cells. Now the question is that are these differences big enough to suggest an independence or an association? Are these differences big enough uh, so that we are able to reject the null hypothesis? You remember we talked about alpha level and p-value, and we set it at 0.05. So we go to the chi-score test table, and then we look at the p-value here. You remember I told you if the p-value is below 0.05, then we can reject the null hypothesis. The null hypothesis was stating that there is no relationship between these two variables. So our p-value is rejecting that null hypothesis. So there is a relationship between stress before treatment and recovery chance. So if you look at the contingency tables, you could see that people who had a higher stress before treatment, they had higher recovery chance. If you look at this cell here, so we expected about 8.5, but we observed 12 people in that cell. On the other hand, if you look at this cell, Uh, we expected again 9 people, but we saw only 5 people. So, uh, yes, there is a relationship between these two variables. And once we look at the contingency table, we can have our interpretation and we can dig further into the table and see where the relationship is. But this is a bit tricky, once we say that, well, there is a relationship, but that doesn't really mean so much because we don't know whether that relationship, that effect is a big effect or not. We're just saying there is a relationship. But that's why we need an effect size value. Effect size is a measurement of a strength. So once you see a relationship, you need to report how strong that relationship is, whether it's a small or big effect. So the value we want to report is Kramer's V, which is the most popular value we report with chi-score test of independence or association. It's a value which ranges from 0 to 1. 0 means no strong relationship. 1 means perfect association. 1 means that the strength of the relationship is perfect. So ours is somewhere in between. This is a substantial amount of strength, which is very good, is not perfect, but at least it's showing that the strength of the relationship is somewhere in between. So in the next slide, I'll tell you how to report the result and how to interpret that. So that's basically the way it's done. You put the variables here in the row and column of the contingency table. It doesn't really matter how you put them, the order. I mean, recovery chance could go here and the stress could come in the columns. It doesn't matter. So in the test, we want the chi-square test, and then we want the uh, Kramer's V effect size. And finally, you also click on both observed counts and expected counts, because later on, if you want to do the interpretation, looking at the expected counts would help you come up with a better interpretation. This is how we present the results. So if you do such a test, you also report the results more or less like this, which is APA style. So you need to report degree of freedom, you need to report the value of chi-score, and also you need to report the p-value, which you can find all of them in these tables. So all these values without the Cramer's V are basically useless, because if you find a relationship, we never know how strong that relationship is. So you need to report Cramer's V, which you can find in the table. I just put it here. And then you basically add a sentence about the interpretation of the results, which here is like people with higher levels of stress uh, seem to show higher levels of recovery success, which is kind of counterintuitive because this data set is just not real. I emphasize again, what you see here is not at all true and may not be true in the real context where you're working. There are also two main assumptions you need to check before you do a chi-square test of independence or association. You need to make sure that uh, your expected frequencies are sufficiently large. The rule of thumb says that you should have at least five in expected frequency in each of those cells I've just showed you. And the second assumption is that uh, the data points should be independent from one another. So uh, this is also very important because we want to make sure that if you recruit one participant, that participant is kind of independent from other participants, or in other words, one data point is not influencing the other data point. This is also very important. You need to check. But most of the times, if your if your design is between subject design, so most of the time the data are independent from one another because you have different participants. So there is a high chance that the data are independent from one another. Well, what happens if these assumptions are not met? For example, no, in some of research studies, you can't really get a big sample, so you don't really have access to big populations or samples. So your sample size is very small. So accordingly, you will have small expected frequency. So if that assumption is violated, then you can use a Fisher exact test, which is a very robust test. You can use these tests. It's just exactly the same procedure like chi-square test of association, and then you'll find um, the thing here. So you basically click on this, and then instead of a chi-square test of association, you'll get a Fisher's exact test. And you can also have the chi-square test as well, and then compare the result with Fisher's exact test. But if you have a small sample size, you don't need to worry. This is the way to go on. And then how about the second assumption? Again, you sometimes the data are not independent. So one of the assumptions with chi-square test of association was that the data have to be independent, but sometimes you get data from the same participants in a longitudinal study. For example, um, level of stress, whether they were stressed or not before the treatment, and level of stress after the treatment. Once you had the treatment, after the treatment, you want to see whether they were stressed or not. So these two variables are categorical. You want to look at the association between these two variables, but you could easily see that the data are not independent because the data are coming from the same person. So the second data is highly correlated with the same data because they're coming from the same person. So if you have such type of data which comes from a uh, within subjects design, this is not between subjects. This is absolutely within subjects. If you have such type of data and uh, your data type is categorical, then you can easily use the McNemar test. So now let's see how we could do the McNemar's test in jamovi. So we go to frequencies, and our design was a within subjects design, so the samples were paired. So we measured the stress before treatment, and then we had treatment, and then we measured the participants' treatment after uh, the participants' stress after the treatment. So this is a paired sample design or within subjects design, and then it violates the assumption of independence. That's why we cannot use a normal chi-square test. So we need to use a McNemar test. So you click on McNemar test here, and then you'll see a, a figure like this, and then you put a stress before treatment, which is one of the variables here, and then you put a stress after treatment here, and then that's basically what you get. So our hypothesis was that stress before treatment and stress after treatment are not related at all. And then we put our alpha level at 0.05. That was the criterion based on which we want to reject or either not to reject the null hypothesis. And then we do the McNemar test in jamovi. And then we go to the McNemar test table here, we'll see that is again is not significant, but it's borderline because it's still above 0.05. How to interpret that? You can easily see that the number of people who said they didn't have stress before treatment is 15, and those people who said they had stress before treatment is 15. So it's very equal before treatment. But if you look at the stress after treatment, you could see that more people are having stress after treatment. So that's mm, it depends on you how you interpret that in the context of your study. But as I told you, this data is just made, it's not real, so it doesn't mean really anything. But you could easily see that we see a difference between stress before treatment and a stress after treatment. More people are saying that they had a stress after treatment. And the p-value here also kind of is a trend and is also kind of showing that. So this is basically how we do the McNemar test, and then you already know how to present the results. I'm not going to talk about it again. You basically need to report the McNemar value here, 3.5, degree of freedom, and p-value. You could also present this contingency table. We come to the end of this session, but before we end this session, uh, these are my expectations. I expect you to be able to analyze categorical data using the two types of chi-square test I talked about. You need to be able to decide when to use each of them. So, and also if the assumptions of the chi-square test are not met, then you need other tests such as Fisher test and McNemar test. You need to be able to know when to use these type of tests. You need to be able to report the tests from these results and also perform these tests in Jamovi. So this is the end of this session. Hope to see you next session. Bye bye.